Hi everyone. Let's look at graphing a little bit more with vertical and horizontal stretches and compressions. We'll start with vertical stretches and compressions. You can see in the figure from your ebook the general description of each type of vertical transformation. If it's a vertical stretch, then you're multiplying by a number, multiplying your entire function by a number that is greater than 1. If it's a vertical compression, you're multiplying your function, which is your y values, by a number that is between 0 and 1. So smaller than 1, but definitely positive. Okay, look at the parabola example I've given you from your ebook. You can see that the blue graph is the original, y equals x squared, and that if I multiply all the y's by 4, the point 0, 0 would not change because 0 times 4 is still 0. But if I were to take a specific look at the point 1, 1 on the original graph, and I multiply the y coordinate of that point by 4, then my new point on my vertically stretched graph is the ordered pair 1, 4. Okay, so again, the number in front of the entire function, when it's multiplied, is considered a vertical stretch or a vertical compression if it's positive and smaller than 1. So take a look at the graph of y equals 1/4 x squared. Again, the point 0, 0 remains the same because I'm multiplying all the y coordinates by 1/4. The original point 1, 1 on the graph of y equals x squared, the blue graph, would become the new ordered pair 1, 1/4. Okay, taking the example I gave you in the last video segment, the line segment through 0, 0 and 2, 1, and that's our generic f of x. If I wish to graph y equals 2 times f of x, and I'll do this in blue, then what I am saying is I intend to multiply all the y values of the original by the factor 2. 0, 0 would therefore not change because y equals 0 times 2 is still y equals 0. The ordered pair 2, 1 would move or translate to the position 2, 2. Now that's not a shift. It's called a vertical stretch. So all of the y's have been stretched by multiplying by 2. If instead I multiply by 1/2, 0, 0 still doesn't go anywhere because the y coordinate is 0 times anything is 0. But the ordered pair 2, 1, if I multiply the y by 1/2, will become a new ordered pair 2, 1/2. Okay, so again, multiplying by a positive number bigger than 1 is a vertical stretch. Multiplying by a positive number smaller than 1 is a vertical compression. Now on to the horizontal guys. Just like with horizontal shifting, the horizontal interpretations end up being somewhat the opposite of what you expect. So for example, if I am multiplying the x coordinate before I substitute it into the function by a number bigger than 1, that might look something like this guy. Y equals root 2 times x. So 2x replaces x. That is the interpretation of a horizontal compression. You'll see in a minute why this looks visually like a compression. Likewise, if I replace x with a number times x and the constant is positive but smaller than 1, this becomes a horizontal stretch. Okay, so here would be an example. X is replaced with 1/2 x. Okay, now this time your graph y equals the square root of x. I've given you this nice image in blue. So in green I'm going to do y equals the square root of 2x. Now you can simply plot points to see this, but I want you to do so strategically. For example, we can do this one easily. X is 0, still produces 0. Ask yourself here, which x times 2 would produce a nice square root? Well, if I let x equal 2, 2 times 2 is 4, and the square root of 4 is the value 2. So this point would be 2, 2. Okay? Now on your original graph, you had an ordered pair of 4, 2. So what essentially happens with this technique is that you're taking the x, let me do it here, that you have originally, and you're replacing x with something else, in this case 2x, which leads you to the equation 2x equals 4, so x equals 2. So what this means is this ordered pair 2, 2 is where the ordered pair 4, 2 moves, if you will, under this compression. Okay? And if you want to, you can think of this as the graph is pushed back. The y stays the same, but the x's get smaller. Okay? Now, maybe I'll pick, instead of blue here, the color red. So let me just box over this. Alright, so if I'm going to do the square root of 1/2 x, I'm thinking along the same lines. I could just simply plot points, and 0 is the easiest guy to sub in, and I still get 0. Here I can ask myself, which x times 1/2 would make for a nice ordered pair? Okay, now this time I'll do the x coordinate of 2, and if I plot that point, 1/2 times 2 is 1, square root of 1 is 1. Okay, so this ordered pair is 2, 1. And what I would note on my original is that if I had the point 1, 1, where did it go? Right here, where the y is 1. Essentially what I'm doing is taking x and replacing it with 1/2 x. So if 1/2 x were to equate to the value x equals 1, I would know where this position moves, and solving that means it would move to the point 2, 1. Okay, so your graph is as follows. Okay, so the green graph is the square root of 2x, and the red graph is the square root of 1/2 x. So in a sense, the horizontal stretch means your graph is pushed back toward the y-axis. The horizontal compression means your graph is pushed back toward the y-axis. That's this guy, compression. And the y equals square root of 1/2 x means that you have a horizontal stretch by 2 units, meaning the x equals 1 got multiplied by 2 and became x equals 2. Now, since this is a little more involved, I'll create another video with some examples illustrating these techniques with specific problems.